The sunlight warming your skin right now is older than farming, older than the first cities, older than any cave painting. The energy in it was forged tens of thousands of years ago, and today is the first moment it has ever touched the outside world. That sounds impossible. Everyone knows sunlight takes about 8 minutes to reach us, so how can the same light be tens of thousands of years old? Here's the trick hidden in that question. The 8-minute number is real, but it only covers the easy part of the journey. Once light leaves the sun's glowing surface, it sprints the 150 million kilometers to Earth in 8 minutes and 20 seconds, moving in a perfectly straight line at light speed. The slow part happens before that. The slow part happens inside the sun, and it is almost unimaginably slow. Start with a simple thought experiment. The sun's radius is about 700,000 kilometers. If the sun were transparent, if its interior were empty space, a photon born in the core would fly straight out to the surface in roughly 2 seconds. 2 seconds to cross an entire star. That's the pace light wants to travel at. But the sun is the opposite of empty. Its core is one of the densest, most crushing environments in the solar system. Consider what a newborn photon is actually born into. At the sun's center, the temperature is about 15 million degrees Celsius, 27 million degrees Fahrenheit. The density is around 150 grams per cc, roughly 8 times denser than solid gold. Yet it isn't solid. It's a searing plasma of bare nuclei and free electrons, packed so tightly that light cannot get anywhere. So what happens to a photon trying to escape? It runs into a wall almost immediately. In this dense plasma, a photon travels only a few millimeters to a few centimeters before it slams into a particle, gets absorbed, and is instantly re-emitted, but in a completely random new direction. That tiny distance has a name, the mean free path. And then it happens again, and again, millions upon millions of times. This is the heart of the answer, and it's called a random walk. Picture someone so lost that every single step points in a random direction, sometimes toward the door, just as often back into the room. Take enough random steps and you barely drift anywhere. That's exactly what the sun's energy does. Each absorption and re-emission scrambles the direction, so instead of a 2-second dash, the energy staggers outward a few millimeters at a time, over and over. How long? The honest answer is that it depends. And that's part of what makes this beautiful. Careful solar models put the crossing time somewhere between about 10,000 and 170,000 years. A commonly cited average is around 30,000 years. The exact figure isn't fixed, because it depends on how opaque each layer of the sun is, and that even changes slowly as the sun ages. But every serious estimate lands in the same jaw-dropping range. Tens of thousands of years to travel a distance light could cross in seconds. Now here's a subtlety that changes what the sunlight even means. The photon born in the core isn't the photon that warms your face. In the core, fusion releases gamma rays, the most energetic light there is. A single gamma ray photon carries between about 1,000,000 and 1,000,000,000,000 times the energy of a visible light photon. Every time that energy gets absorbed and re-emitted on its long, random walk, it tends to come back out at lower energy. One brutal gamma ray gradually becomes a whole shower of gentler photons. Until, near the surface, the energy finally emerges as the visible light we can see. So the light you see isn't the original ray. It's the ancient, mellowed descendant of energy made in the core. And that energy is relentless. Every second, the core fuses about 600 million tons of hydrogen into helium, turning roughly 4 million tons of matter directly into energy, pouring out power at nearly 400 trillion watts. All of it begins the same slow crawl outward. Follow the path, and the sun reveals its layered structure. From about 1/5 to 7/10 of the way out lies the radiative zone, where energy inches along by that endless absorb and re-emit dance. Above it sits the convective zone, about 200,000 kilometers deep, where the plasma finally starts physically boiling. Vast columns of hot gas rise, cool, and sink, carrying heat like a pot at a rolling boil. And then, at last, the photosphere, the visible surface, a comparatively cool 500 degrees Celsius. Only here does the gas thin out enough to become transparent. Only here can light finally leave freely and race into space, which sets up one last striking contrast. Fusion in the core doesn't only make light, it also makes neutrinos, ghostly particles that barely interact with matter at all, because they almost never get absorbed. Neutrinos don't random walk. They fly straight out of the core in about 2 seconds, then cross to Earth in about 8 minutes. So when a detector deep underground catches a solar neutrino, it's reading a message from the core that's only minutes old, a live report from the sun's furnace. But the light on your skin is a message that left the core when mammoths still walked the Earth. Two kinds of signal from the very same fusion, in the very same instant. One arriving fresh, one after tens of thousands of years. The difference is nothing but how easily each one slips through matter. So the next time you feel the sun's warmth, remember, the last 8 minutes were the easy sprint. The real journey was tens of thousands of years trapped inside the sun. Ancient light, touching the universe for the very first time.